from Queen's University in Belfast. And let me start thanking Kike and Michael and Lucas and all the organizing committee for having me around. It's my first time in Bilbao. And just to give you the time to get used to my weird accent and probably just to give you the time to, to sit down, let me tell you a couple of things about the place not I come from, but the place I work in. So this is Europe, no? Yeah? And in Europe there is this, this country. The UK. It doesn't include part of this island. And this region here is called Northern Ireland. And Northern Ireland is where Belfast is, which is this dot there. And currently the big debate is whether or not Northern Ireland is in Europe. To me, UK is in Europe, and that's a statement, and that's it, and it will always be, okay? So Belfast is a nice place, and I found it has a few similarities with Bilbao, quite a few. So first of all, starting from the trivial one, they both start with B, and that's fine. But if you then look at how much it rains in both cities, you find some similarities. Actually, I was pleased that it rains here more than what it does in Belfast. Apparently, so the statistics come from Wikipedia, so they must be true, right? But it seems that it rains here much more than what it does in Belfast. But we basically have worse, shitty sort of summers, no, with respect to Bilbao. And you shouldn't be fooled by the nice weather that is outside. We also have that, right? So this was on the 26th of March 2009, and we are waiting for the next day. It doesn't happen very often, but final similarity, I think, before digging into the physics. A couple of more, Penchant for fancy architecture, no? So there is the Guggenheim Museum here. We have the Titanic Museum in Belfast. Yes, the Titanic was built in Belfast. It sank somewhere else, but it was built in Belfast. And I found that there is a Belfast Titanic Society. And that's not the funny thing. You're smiling now. Read the motto, right? The word commemorates the tragedy. Only we can celebrate the triumph. And I always looked for which sort of triumph they are talking about. I know the answer. Yeah. Correct, and it sank. And the Irish were happy with that. Final similarity, apparently people in the Basque Country and people in Northern Ireland, they share some similar taste for fashion. Balaclavas and Basque. I mean, there are differences, definitely, but I mean, you can see the pattern, and without the machine learning approach, actually. Anyway, so enough with so I think you are used to the way I talk by now. So let me thank the guys that contributed to this work. So the main star is Luca Innocenti, who is a PhD student of mine in Queens. Then there is Leonardo Banchi at Imperial College London now. And these two chaps, with me, we just stayed and looked at what the amazing thing that these two guys together, they did. Now, talking to the principal investigators in this room, if you have money and you want someone amazing, hire Luca. He's great. Anyway, so I hope I'll be able to give you just a taste of what they did. Okay, so by the way, the talk is very timely, and this morning the paper accounting for what I'm going to discuss came up to the archive. So whatever I will not be able to discuss because I'm not good at that, you will find it in this paper. Okay, so this is going to be a straightforward talk. And the question that I have is really, linear. It's really straightforward. So suppose that I want to synthesize a gate. I want to realize a gate, G, from a generator, an Hamiltonian that is Hg. And I want this Hamiltonian to comprise only operations that come from an assigned set of operations. I don't want any possible operations. I just want a set, a subset of them. So again, because I'm a simple-minded person, or as my daughter said, I'm stupid, let me illustrate it in a very, very simple way. So suppose that this is the gate that I want to realize. So is red, it's a polygon of some form, okay? And suppose that the gates that I will need to use in order to decompose this gate, right, so and achieve the effect of the polygon there, the red polygon there, all these fancy, nice, and colored shapes that I have here. But then, we had 3 experimental talks before me, and these guys only have a limited number of operations that they can do in a cheap and convenient manner, inexpensive manner. So I don't want to use all of them. I don't want to use the pentagon, for instance. It's too complicated. Let me use a restricted set of operations. And this is what I will call in this talk gamma. And just for the sake of the talk, we assume that these are they are basically realized by the interactions, by the evolutions that an experimentalist can realize easily and cheaply in the lab. Okay? So I don't know. Christoph Wunderlich yesterday talked about an ion and interacting with microwaves, and you have basically the Jaynes-Cummings model there, right? Same for Stefan Philipp. This morning there were cold atoms, and you have only a subset of the possible interactions that can be considered when you work with a cold atom system. Yet you want to realize something as complicated and ugly as that. And most of the time, what you need say complicated gates, so multi-qubit gates. Can I implement them? Can I realize them? By using only a subset of evolutions, a fixed subset of evolution that might be dictated by the experimental setup that I have to deal with. Okay? So the messages that I would like to you to take home are the following. Yes, you can, and we are going to identify 3 conditions to produce a gate, actually an Hamiltonian H tilde, that comprises only operations drawn from a chosen subset gamma, and that realize, nevertheless, precisely the gate that you want to realize. The set of 3 conditions are tough, but they help designing a numerical supervised learning based approach that will help us basically achieving the task that we want, and I will illustrate it with a set of examples, mostly with 3-qubit gates, but the paper goes beyond that. Okay, so what is the general methodology? Okay, and I'm very lucky because yesterday and this morning, most of the talks introduced all I need to discuss. So most of what I'm going to say, if you feel a sense of déjà vu, is normal. You have heard it from other talks. Okay, so this is the gate that I want to realize. This is the Hamiltonian, the effective Hamiltonian that implements it. And I've rescaled things in a way that basically the time at which I achieve the gate that I want is equal to 1, okay? What I can do is that I can spectrally decompose it. So lambda here is the matrix that embodies the eigenvalues of this gate. Nothing fancy at this stage. I can take the log, the principal log of it, and get an expression for the Hamiltonian, the effective Hamiltonian that realizes this gate. And as I said, this effective Hamiltonian most likely comprises what I call feasible and unfeasible interactions in the sense of what I said before. So unfeasible interaction for the specific setup that one has in mind or that you are working with. And I don't want these unfeasible interactions. I want to find a new Hamiltonian, Hg tilde, built using only my green squares, but that achieve precisely the gate, the operation, the transformation that I had in mind. What do we not want? Okay, so what can we give up with is time-independent Hamiltonian, so I don't want any time dependence. I want time-independent object. I don't want to plug in my register, which is already a mess. I don't want to plug in additional ancillary systems. So I don't want to use extra resources. And I don't want to rely on complicated quantum control approaches. Okay, so I don't want to time gate my resources. What do I want? I want to satisfy these three conditions. And if you want, these three conditions embody basically the pillar of the paper. Okay, so very trivially, no, Hg tilde must contain only the evolutions that are feasible, as I define them. Then I want the principal generator, right? So the effective Hamiltonian that I got by taking the log of my gate G to commute with the one that I want to get, sorry. And the third condition that I want is that the eigenvalue of the difference between these two matrices, between these two Hamiltonian, is an integer number of times 2 pi. Why do I want that? Because if I get these three conditions, and the first one is very trivial, no, it's trivial. We have discussed it already. The other two are sort of tougher, but the second one is not that much. I mean, it's not too restrictive. But if I achieve basically condition 2 and 3, then I did it. Okay, then I can get my gate G and decompose it in a way that basically G itself is realized by that expression. And given that Hg tilde and Hg commute, basically the effect of Hg is cancelled, and I get precisely what I want. The demonstration is in the paper, and I don't want to waste time with that. So please read the paper. But what I want to give you is basically the gist of it. Okay, so given G, I'm basically looking for the addition to the principal generator of my gate of something else. So additional terms, this something else must be such that I fall fully within the category of feasible Hamiltonians that I can realize in the lab, and automatically satisfy condition 2 and 3. Is that possible? Yes, it is, and the approach to follow is the following. First of all, the three conditions that I have stated, as I said, at least one of them, the last one, is tough, but not always. I mean, there are cases, for instance, a Toffoli gate or a Fredkin gate, where you can actually solve the problem analytically and therefore get an analytical strategy for simulating for achieving, actually, not simulating, but getting the Toffoli gate with the restricted set of Hamiltonians that your physical system, that your physical setup allows you to do. In the worst case, when the analytical approach is unfeasible, these three conditions help you identifying some efficient starting points, some very useful starting point for numerical optimization. And this is where I'm going to concentrate. As I said, I'm not going to go through the analytical demonstration of the statement, but I want to illustrate what the numerics does. Okay, so the starting point is to choose a parameterization of the Hamiltonian comprising only feasible terms. So terms coming from my subset gamma. Then what I need to do is to use condition 2, the condition on the commutativity between the principal generator and the one that I want to achieve, to reduce the number of parameters that enter into this parameterization. Here, lambda is a vector of numbers, basically coupling strengths, magnetic fields, stuff that define the Hamiltonian of interaction that you want to use to synthesize your gate. Then you need the non-trivial step, which means enforcing the third condition, right? So the difference, the eigenvalues of the difference between the principal generator and the guy that I want to find must be an integer number of times 2 pi. So basically, I have to solve an inverse eigenvalue problem. And when I have a sizable number of parameters, this is very, very tough. So I want to bypass the solution of the inverse eigenvalue problem using a supervised learning approach. Okay? So this is going to be the focus of the next couple slides. What is the strategy that we have followed in the supervised learning approach? So we decomposed our Hamiltonian. So I dropped the PEDX G and the tilde here, no? So just for easiness of notation. But basically, this is the guy that I want to get, right? So this is the Hamiltonian comprising only feasible terms. So now you can parameterize and decompose the Hamiltonian in this way, where these operators, so I, are needless to say your mission operators, and the lambda I, for the sake of simplicity, real parameters. Then let's compare what I will get by exponentiating this parameterized guy with what I want to get, right, with the gate G that I want to get. And let's do that, so let's basically calculate this fidelity for all possible input states. So I'm not happy with just one input state that allows me to achieve the result of my gate. I want the synthesis to be effective regardless of my input state. So I want to look for the set of parameters lambda naught that give me a fidelity equal to 1 for all possible input state psi. The algorithm that we are going to use is, starts with an initial guess for the set of parameters lambda that we have to use to parameterize my alleged Hamiltonian. You generate a random set of input states, and you actually do it in batches, in mini batches, okay? So K here is a label for mini batches of input states that I'm going to use to compute a gradient, okay? So this is, again, basically gradient descent-based approach, but a stochastic one. Why a stochastic gradient descent? Because, as I stressed, I want the fidelity to be equal to 1 regardless of my input state. And this is precisely what the stochastic approach, the stochastic version of the gradient descent allows me to achieve. I don't need to teach you that, okay? After computing the gradient, I update my choice of lambdas using momentum gradient, okay? So, and basically I have to follow the following set of equations, right? So my gradient is used to determine this parameter nu that depends on gamma and eta and the previous value that nu had. And then I update lambda to lambda plus nu. And these two parameters, gamma and lambda, are called momentum term and learning rate. And these are two numbers that you have, again, to guess at the beginning and possibly adjust step by step. Okay, for instance, typically the learning rate is reduced in value as you progress in the evaluation of the gradient. And then finally, you repeat basically from step B forward until you achieve a satisfactory value of the fidelity. In my case, it's very strict. I want a fidelity equal to 1. Computationally here, and again, it's something that I don't need to tell you, the difficult part here is the inefficient part is the calculation of the gradient. And we did that with basically automatic derivative with error backpropagation, which is, again, say a numerical strategy that codes like Theano or PyTorch or TensorFlow have embedded, and that allows you to limit or keep at bay the error induced by the evaluation of the gradient. Okay, you do that, and then you want to. No, I want to show that it works, right? So, couple of examples. I think, Peter, am I doing with time? Okay, good. So, couple of examples of instances, starting with the 3-qubit quantum Toffoli gate. Okay, so a control not, very important gate for reversible computation. If you compute the Hamiltonian, not the principal generator, the effective Hamiltonian that generates this gate, you realize that you need both 2-body and 3-body interactions, right? So you have this term Z, X that is there. And suppose now that Fabio comes in and says, oh, forget it, I don't want three-photon coupling, the treater is too expensive, I shall do it with a beam splitter. So 2 photons only, okay? So 2-body coupling. Can we do that? So I shall define my set gamma of feasible gates as gates comprising only 2 qubit terms. Then what I do is that I start parameterizing my desired gate, right? So my desired Hamiltonian, the guy that I want to achieve, using only 2 qubit interactions. You feed that into the numerical machinery that I've illustrated, and you face immediately the problem of having 37 parameters to deal with. But as I said, the moment you enforce the second condition that we have identified, you reduce the number of parameters quite dramatically, right? So you have to discard all the terms that make these parameterization not commuting with this Hamiltonian. So this reduces quite a lot the number of parameters that you have to deal with, all the way down to something like 13 parameters. So you can be basically content with an expression, an horrible expression like this, where now your problem is, let's get numbers for this coupling strength. And this is what the supervised learning approach does it. It's too large for an inverse eigenvalue approach, so you plug it into the numerical calculation, and you actually do get more than a single solution, okay? So you actually get more than a single way of synthesizing this gate, right, the generator of the gate that you want, and this is just an example of it, okay? So if you didn't get it, I slightly changed my notation here, Z, X, there is no, yes, and Y, the Pauli spin matrices that I indicated as sigma before, but it's pretty straightforward, okay? So, for instance, a green line here is the set of all my 2, 4, 6, 8, 9 parameters that enter into this decomposition, while the, I'm colorblind, so is this red, guys? Yes, the red one is yet another set of parameters. So you have many different ways of actually achieving the very same task. And you can then have fun and try what happens with the Fredkin gate. Okay, so control swap gate, equally important. The principal generator looks, again, something horrible like that. Again, you comprise 3-body interaction. Let's, again, suppose that I can only do it with 2 qubit interactions. And I will actually ask more. I will want to do it with only what we call diagonal operations, which means, for instance, qubit 1 and qubit 2, or qubit 1 and qubit 3 must have the same Pauli matrix, okay? So you don't see crossed one, no? You don't see qubit 1 having a Y Pauli matrix and qubit 2 having a Z Pauli matrix, okay? So if 1 has a Z, also 2 has a Z, and 3 has a Z. And you can do that, okay? So you plug this problem into your numerical calculations based on supervised learning, and you get the decomposition that I have illustrated here. And again, this is only one of the possibilities. There are quite a few. We have chosen something like 6 or 7 instances. And you can actually do more. No? You can actually track what happens to these parameters, to the value of these parameters, which I stress. These are the numbers that allow you to get a fidelity equal to 1, exactly equal to 1, okay? So you can actually track what is the behavior in time while you repeat, while you iterate your algorithm in time. And this is what happens, no? So the parameters, say, change sometimes wildly, sometimes more smoothly, and then achieve a steady state value that is when the fidelity hits the value of 1 and stays there. Okay, and this is more or less it. I mean, if you go through the paper itself, you will see we discuss a few more results like this Toff-Fredkin gate, and also a multi-qubit gate. So we went beyond the 3-qubit limitation, addressing the synthesis. Sorry, it's a very difficult word for me, of a 4-qubit gate, and we have results for other interesting problem involving more, definitely more than 3 qubit only. So there will be some more results coming up in the next future. And probably what I want to close this talk with, if I still have a minute, yes, is a couple, basically one problem already, Fabio discussed already where is Fabio? Fabio somewhere? Yeah, Fabio already mentioned the work that is ongoing between Belfast and Rome on the engineering of states through orbital angular momentum and the work of Tyra in this respect. So what I want to mention is something that we are doing with Riccardo Sapienza and Sylvain Giguin. Riccardo is at Imperial, and Sylvain works in Paris. So what we want to do is to use a combination of two ingredients, machine learning on one end and disordered systems on the other. Okay? So these guys, both these guys, they can manage disordered systems. Here is an instance. Actually, I can give you a picture of the experiment. So this is this is basically a nano-engineered structure, nanostructure, photonic nanostructure in one of the in the lab of Riccardo in London. So these are basically networks across which light can flow. Okay, so a photon, for instance, entering this structure from here can follow one of these two paths, the blue one or the red one, as well as many other paths across the structure, just like the maze that was mentioned by Fabio in his talk, okay? Or a random walk, depending on what the light which path the light decides to follow. And you can control, actually, the path itself, because each node in this structure is basically a scatter. So, basically the strength of the scattering experienced by a photon impinging on one of these nodes can be controlled from outside thermally. Okay? So in a way, you can guide the light through this complex nanophotonic structure. You can also do something else. No? You can input light into this structure through a source, and you can shape the wavefront of this light. You can do that with a magical system. For me, I'm a theorist, called Spatial Light Modulator. I still have to understand how this guy works, but that allows you to shape the wavefront of a photonic signal almost as you want. Okay? There are limitations, but it works almost at will. So what we want to do is the following. We want to use the possibility of manipulating the nanostructure through this thermal control of the rate of scattering of the nodes in the nanostructure itself. And we want to use the shaping of the input light through SLMs, so through spatial light modulators, and embed in that a supervised learning protocol to devise the best strategy that we have to implement, the actual optimal strategy that we have to implement, in the shaping of the wavefront, and in the coupling among the scatters, basically in the way the scatters affect light, to achieve an output, a transformation to the input encoded in the wavefront of the light in a multidimensional system. Okay, so in a very, very large Hilbert space, spanned by basically the modes, the number of modes that you can control in this nanostructure. This is work in progress. Hopefully, if the organizer organizes a second version of this talk and they want me back, I will be able to report on that. So Peter's patience is expiring, so this is the group that suffers my tantrums in Belfast. These are the guys that put the bread on our tables, and we are grateful to that. And if I can take half a minute of shameful advert, we have a two-year postdoc position in Belfast. So if you know of any of your students or postdocs that enjoy a bit of bad weather and good beer, just let me know. Okay, so thank you so much.
Thank you.
Sorry.
Questions? Can I start with one? I probably missed this part. When you do the gradient descent, you feed in random states.
Yes.
So you choose them with a hard random measure.
Yeah. Uniformly with.
Did you consider doing some optimization there? So picking the states
that
would be good.
We didn't cherry pick the states.
Okay.
We just went basically blindfoldedly on the random state.
Like a very pure pack learning.
Yeah. So it could well be that if you do what you're suggesting, you actually improve the efficiency.
Yeah.
I mean,
Okay.
You improve the protocol itself.
Nathan?
So, quick question. How is this algorithm any more of a supervised learning algorithm than GRAPE?
Say it again, sorry.
Okay.
I have a cold and I don't hear very well.
Okay, so you mentioned that this is a supervised learning algorithm, but it feels more like an optimization algorithm. So I'm curious, how conceptually different is it than GRAPE?
Didn't think about it. I mean, I don't know. We just didn't think about it.
Then okay, another quick one. How for the TOEFL gate, similar
Yes.
to Peter's suggestion, why didn't you just feed in every computational basis state? Because that would be sufficient.
Oh, sure. Yeah, you can do that. I mean, it was mostly just for illustrative purposes. I mean, we just picked up a gate that is relevant, and we did it again, blindfoldedly mostly. Okay, so you can do much more refined strategies than that, surely. But this was simply for illustrative purposes. So there is no big reason behind it. About the GRAPE question, I mean, we can discuss it. I mean, we just didn't think.
Okay, more questions? Just a note on this GRAPE. So GRAPE is more for online control of a system, no? Whereas here you do the search in advance, and then you actually implement it and do some control later. So I think the scope is different.
That, honestly, we didn't put any thought about on it, so we can surely discuss.
All right, more questions? If not, then let's
Thank you
thank the
again.
speaker and thank you.